Welcome back to Signal 2030, where we explore the scientific breakthroughs shaping our future. If you've been with us on this incredible journey, you know we've been tracking the future of energy, and particularly nuclear fusion, with intense interest.
Indeed. It's been quite the ride.
It really has. This is part 5 of our fusion series, and today we're shifting gears a bit, moving from the pure science to something, well, profoundly impactful. Do you remember that landmark achievement back in 2022? The fusion ignition at the National Ignition Facility, NIF, where they actually got more energy out than they put in, just for a moment.
Oh, absolutely. A pivotal moment.
Exactly. That wasn't just some interesting science footnote. It genuinely transformed the whole conversation around fusion.
It really did.
For the first time, the central question moved from if fusion energy is even possible to when, how, and maybe most critically, at what cost. It can actually be brought to the grid and, integrated into our society.
That's the crux of it now, isn't it? The practicalities.
Right. So our mission today is to unpack the profound societal ripple effects of viable fusion energy production. We're looking at how this monumental innovation could fundamentally reshape our energy sector, our global economy, and maybe even the very fabric of our daily lives.
It's a huge scope.
It is. We'll be diving into its potential for clean power, its remarkably small land footprint, its ability to provide that high-grade industrial heat.
Crucial for heavy industry.
To secure our water supply, maybe even open up new frontiers in deep space exploration. And we'll also explore the creation of an entirely new, high-skilled workforce.
It's fascinating how rapidly the discussion has evolved, hasn't it? From being almost exclusively a realm of fundamental scientific inquiry.
Right, big government labs mostly.
We're now firmly in the territory of strategic commercialization. Fusion is no longer just a distant theoretical concept. It feels like a tangible reality on the horizon.
It feels closer than ever.
And as you highlighted, its role in our future energy system is poised to be unique and, frankly, absolutely critical. It's not envisioned as a simple one-to-one replacement for existing renewables like solar and wind.
Which is an important distinction.
A very important one. It's seen more as an essential complement. Think of it as the unwavering backbone, providing stable baseload power, ensuring grid stability in a world that absolutely needs to be fully decarbonized. It's that constant on-demand foundation.
The power that's always there when you need it.
Exactly. But the impact extends far beyond just keeping our lights on.
Okay.
This is where the multifaceted nature of fusion's potential truly comes into focus. Beyond generating electricity, fusion offers the ability to provide high-grade industrial heat directly to heavy industries and to produce clean hydrogen at scale.
That's right.
These capabilities are crucial because they offer pathways to decarbonize sectors that are incredibly challenging to tackle with electricity alone. Think steel production, cement manufacturing, long-haul transportation.
The really tough nuts to crack.
Precisely. So we're truly talking about a technology that could touch everything from our power sockets to our water taps, and like you said, even our most ambitious aspirations for space.
That sets the stage perfectly, because if we're exploring profound societal impacts, we have to start with the economy. It just makes sense.
Economics drives so much.
For decades, fusion research was almost exclusively confined to those large government-funded national labs and international collaborations. It was, basically a public science project.
A very expensive one, too.
Ah, yes, a very expensive one. But what we've witnessed in the last decade, and especially in just the last few years, is a complete paradigm shift. Some are calling it the new energy gold rush.
That term is definitely being thrown around.
But what precisely was the tipping point? What unleashed this, unprecedented influx of private capital? And are there any, counter-arguments, concerns about a potential bubble or maybe overpromising?
That's a critical question, and you're right, the shift is undeniable. It's really quite stark. By the end of 2020, private capital invested in fusion startups had already reached a notable $2 billion.
Which was already significant.
It was significant, yeah. But then, as you suggested, it just exploded.
Yeah.
By early 2024, that total private investment had soared to over $7.1 billion.
Wow, that's incredible growth.
It really is. This isn't just a trickle, it's a flood. And there are indeed clear drivers behind this surge, but also, yes, valid considerations about hype.
Okay, so what are the main drivers?
First, the scientific breakthroughs, like NIF's ignition achievement we mentioned. That provided concrete validation that net energy gain is physically achievable.
De-risked the science, essentially.
Exactly. It fundamentally de-risked the underlying science for investors, moving it from pure theoretical possibility to a demonstrable phenomenon. Second, There's the urgent and growing global need for clean energy solutions, driven by intensifying climate change concerns and, frankly, geopolitical energy security considerations.
Huge market pull.
Massive market pull. And third, the sheer market potential itself. We're talking about a multi-trillion-dollar opportunity. That's simply too large for venture capital and strategic investors to ignore.
Trillions. Okay, that gets attention.
It certainly does.
Yeah.
Now, regarding concerns about a bubble or overpromising, it's a valid point.
You hear it sometime.
You do, especially given the aggressive timelines some private companies are projecting. However, unlike previous periods of fusion hype, this surge is underpinned by a level of scientific validation and, crucially, a convergence of global urgency that wasn't present before.
So it feels different this time.
It feels different, yes. And governments aren't just watching, they're actively working to catalyze and leverage this private investment. Take the United States, for instance, with its bold vision for commercial fusion energy.
Right, the PPP approach.
Exactly. Public-private partnerships, PPPs, have become a cornerstone of their national strategy. The goal is to accelerate R&D and enable the construction of a private sector-led fusion pilot plant as early as the 2030s.
That's ambitious.
It is. A key instrument here is the Department of Energy's milestone-based fusion development program. It received an initial $46 million.
How does that work exactly?
Well, this program co-invests with private companies. Government funds are released as these companies achieve pre-agreed technical and scientific milestones.
So it ties funding to actual progress.
Precisely. It's a smart way to use public money to de-risk private investment and focused efforts, while also imposing accountability. Industry advocates like the Fusion Industry Association, the FIA, are even pushing for more.
More funding.
Yeah, suggesting a one-time supplemental appropriation of $3 billion. This would fund essential R&D facilities, like a dedicated neutron source for advanced materials testing, which is critical.
We'll probably come back to materials.
Oh, we will. And it would significantly expand that milestone-based PPP program. This really underscores the synergistic partnership needed. Foundational public science, which is often too slow for the market.
Yeah.
Combined with private commercial drive, which on its own might lack the long-term capital and foundational research. This blend is seen as the fastest, most effective path to commercial fusion energy.
Designed to mitigate the bubble risk, maybe.
Exactly. Mitigate the bubble risk by tying funding to milestones, and also mitigate the too slow risk of purely public endeavors.
That synergy sounds ideal on paper, but historically, these big public-private collaborations can sometimes get bogged down, right? Conflicting priorities, bureaucracy. What strategies are there to mitigate those risks and keep things moving efficiently?
That's a very fair point. Potential pitfalls exist. The main mitigation strategy often involves those clear, predefined milestones we just discussed, like in the DOE program. It creates a shared incentive structure.
Everyone pulling in the same direction, hopefully.
That's the goal. It's about leveraging the strengths of both sides, the foundational science and long-term vision of government labs, paired with the agility and market-driven focus of private enterprise.
Okay. And on the private side, who are these companies actually leading the charge? What are their unique approaches? Because for you, our listener, knowing these players is key. They're the ones making the bets that shape our future energy.
Absolutely. This new investment landscape has really fostered a vibrant ecosystem. Let's touch on a few of the frontrunners because their choices really define the early market landscape.
Okay, lay them out for us.
First, there's Commonwealth Fusion Systems, or CFS, you've probably heard of them, an MIT spinoff, a leader in developing compact tokamaks.
Compacts being the key word.
Compact is key. Their core innovation is their pioneering use of high-temperature superconducting magnets, HTS magnets.
Okay, what's special about HTS?
Well, these magnets, made from materials like rare earth barium copper oxide tapes, can generate magnetic fields significantly stronger than conventional superconductors.
Stronger fields mean?
Stronger fields mean you can confine the plasma more effectively in a smaller space. This is a potential game changer because it allows for fusion devices that are dramatically smaller, potentially less expensive, and faster to build.
Makes sense.
In 2021, CFS validated this. They successfully tested a large-scale HTS magnet, achieving a world record field strength of 20 Tesla. That single achievement really shifted perceptions of tokamak feasibility.
That was a big milestone.
A huge one. CFS is currently building their demonstration device called Sparkback. It's designed to be the first magnetic confinement experiment to achieve net energy gain Q greater than 1 targeting the mid-2020s.
So very soon, potentially.
Relatively soon, yes.
Okay.
Following Spark, CFS plans to build ARC, its first commercial grid-scale power plant, projected to come online in the early 2030s.
And they've raised serious money.
Oh, yes. Over $2 billion from a blue-chip list of investors: Google, Bill Gates' Breakthrough Energy Ventures, the Italian energy giant Eni.
Heavy hitters.
Definitely. And in a landmark move, signaling the dawn of a real commercial market, CFS signed a power purchase agreement, a PPA, with Google in 2025.
A PPA, to actually sell them power.
Exactly. To supply 200 megawatts of electricity from its future ARC plant. This isn't just an investment anymore. It's a concrete commercial commitment to buy the product.
Wow. Okay. Who else?
Then there's Helion Energy. They're pursuing a different path. Magneto-inertial fusion.
Magneto-inertial. Okay. How's that different?
Their design aims to be more compact than traditional magnetic fusion devices and, interestingly, is being developed for direct energy conversion.
Direct conversion, not steam turbines.
Potentially, yes. Converting the energy of the charged fusion products directly into electricity. This could offer much higher efficiency than a conventional steam cycle, which is a big deal economically.
That would be a big deal. Have they hit milestones?
They have. In 2021, Helion's 6th-gen prototype, Trenta, hit plasma temperatures of 100 million degrees Celsius, a critical target.
100 million degrees. Okay.
Now they're developing Polaris, their 7th-gen machine, designed to demonstrate net electricity production.
And their funding timeline?
Over $1 billion in funding from investors like Sam Altman of OpenAI and Microsoft. And mirroring the CFS Google deal, Helion signed a PPA with Microsoft in 2023.
Another tech giant signing up.
Yes, committing to deliver at least 50 megawatts of fusion power by 2028.
2028. That's incredibly aggressive.
It is one of the most aggressive timelines in the industry, absolutely.
Okay, one more major player.
Let's talk about TAE Technologies. Based in California, TAE is one of the oldest and most well-funded private fusion companies. They're developing a unique reactor based on a field reverse configuration, or FRC.
FRC, that's different again.
It is. It's a linear device, not a donut shape like a tokamak, confining plasma in a self-contained structure. A key part of TAE long-term strategy is to use an advanced aneutron fuel cycle.
Aneutron, meaning no neutrons.
Almost no neutrons, yes, using hydrogen and boron, or PB11. This reaction produces primarily charged particles, which would dramatically reduce the radioactivity of reactor components and simplify engineering challenges related to materials and heat extraction. If they can achieve fusion with it, it's harder physics.
A big if, but big potential payoff.
Exactly. TAE's current device, Norman, has achieved plasma temperatures over 75 million degrees Celsius. They've secured over $1.2 billion from investors, including Google and Chevron, and they have a deep collaboration with Google using AI for plasma stability.
AI being used in system design, just as we discussed in the earlier episodes.
Very much so. So the emergence of these and other well-funded players has created this competitive, milestone-driven environment that's really accelerating progress.
And those PPAs seem critical?
They are absolutely critical. These aren't just investments. They're the first concrete commercial commitments to purchase fusion electricity. This creates a powerful market pull that perfectly complements the technology push from R&D.
Validates the business case.
Precisely. For the fusion companies, it provides a guaranteed first customer, validates their pathway, helps attract more investment. For the tech giants, with their massive, growing energy needs for data centers and AI.
Yeah, their energy use is huge.
It's enormous. For them, it's a strategic, relatively low-cost bet to secure a potential long-term source of clean, reliable, 24/7 power that perfectly complements their huge investments in intermittent renewables like solar and wind.
So it fits their strategy.
Perfectly. This symbiotic relationship between big tech and fusion startups is a powerful new accelerator for the whole field. It fundamentally de-risks the long road to commercialization and signals to the entire investment world that fusion is no longer just a science project, it's being treated as an actionable energy solution.
So the investment is clearly flowing, big tech is betting on it. But this brings us to that crucial, often debated question. Can fusion truly be competitive economically?
The bottom line question.
Right. Because no matter how clean or cool it is, it has to make economic sense in the market. We talk about the levelized cost of energy, LCOE, the lifetime cost per unit of energy, What are the projections telling us? And why such a wide range in those predictions?
You're hitting on the core economic challenge here. And yeah, projecting LCOE for a technology that doesn't exist commercially yet is inherently speculative. There's just no getting around that.
Lots of assumptions involved.
Tons of assumptions. However, various analyses give us a framework for understanding the economic targets fusion must meet to be viable. Some projections are quite optimistic.
Like how optimistic?
For instance, a 2025 study from researchers linked to First Light Fusion, they're pursuing an inertial confinement approach, suggested a mature fusion plant could achieve an LCOE as low as $25 per megawatt hour.
$25? That's incredibly low.
It would be extraordinarily competitive, yeah, potentially undercutting not only existing nuclear fission, maybe around $100 per megawatt hour, but even onshore wind, which might be up to $50 per megawatt hour if you include intermittency costs.
But that 25 LCOE relies on what?
It relies on very novel plant designs with high energy yields, allowing for smaller, much less expensive construction. Big assumptions there.
Okay, so that's the optimistic end. What about more conservative views?
Well, other analyses, like a major 2024 study from the MIT Energy Initiative, frame it differently. Instead of predicting a single LCOE number, they model future decarbonized energy grids to figure out the capital cost at which fusion becomes a significant player.
What cost does it need to hit to compete?
Exactly. Their findings suggest fusion could play a major role, potentially saving the world economy trillions in decarbonization costs, if the overnight capital cost of a first-of-a-kind plant is somewhere between, say, $5,600 and $8,000 per kilowatt.
Okay, that's a target range.
It's a target.
Yeah.
And if costs can eventually be brought down further, maybe to around $3,000 per kilowatt for mature mass-produced plants,
Through learning and scale?
through learning, scale, innovation, then fusion's share of the global electricity market could even exceed 50% by 2100, according to their models.
50%. That's huge. But that cost difference, $8,000 down to $3,000 per kilowatt, that's massive.
It is massive. And this wide range isn't just about different models. It underscores the real battleground. While the physics is maturing, it's the engineering and manufacturing innovation needed to drive those costs down potentially by orders of magnitude that's the true economic challenge for fusion.
So if capital costs stay too high?
If capital costs remain too high, fusion will struggle to compete effectively against other clean, firm power sources. Simple as that.
Okay, so if capital costs are the absolute linchpin, what are the primary drivers pushing those costs up? And what specific innovations are most crucial for bringing them down? And beyond the initial build, what other factors heavily influence that final LCOE?
That's exactly the right breakdown. Let's dig into these cost drivers and uncertainties. First and foremost, capital costs. As you said, the linchpin.
The big upfront investment.
Huge. Just like with nuclear fission, the upfront construction cost is expected to be 60% or even more of the LCOE. And think about why these plants are intrinsically expensive.
Yeah, we discussed previously why this is such an expensive engineering challenge.
That's right. You need specialized radiation-resistant materials. You need massive superconducting magnets, some requiring truly unprecedented scale and precision. Complex vacuum systems, cryogenic systems to keep magnets super cold, high-power lasers or plasma heating systems.
A lot of cutting-edge complex tech.
Exactly. Reducing this initial capital outlay is the central economic challenge.
So innovation is key to cost reduction.
Absolutely crucial. Second point, technological innovation. Commonwealth fusion systems that work on HTS magnets is a prime example.
Right, smaller tokamaks.
Smaller, more powerful tokamaks aim to dramatically reduce the physical scale and therefore the cost of the reactor. Similarly, alternative approaches like KAE's FRC or Helian's magneto-inertial fusion are being pursued with the explicit goal of creating simpler, more manufacturable, and hopefully cheaper reactor designs.
Moving from lab experiments to something like an assembly line.
That's a huge economic lever yet.
Yeah.
Moving from custom, one-off scientific experiments to repeatable, potentially mass-produced components and systems.
Okay, what else affects the cost? Operational stuff.
Definitely. Third, operational factors will be critical. A significant challenge is what's called the high recirculating power fraction.
Recirculating power.
Yeah, that's the portion of the plant's own electricity generation that it needs, just to run its internal systems, the magnets, lasers, heating, cooling, everything. To be commercially viable, a fusion plant has to achieve a very high scientific energy gain, Q scientific, probably greater than 15 or 20 for early plants.
Just to have enough left over to sell.
Exactly. Just to ensure there's enough net power left over for the grid after powering itself. Furthermore, the plant availability, or uptime, is crucial.
How often it's actually running.
Precisely. Frequent or lengthy shutdowns for maintenance, especially for replacing components damaged by neutron radiation, would severely impact its economic output, no matter how cheaply it produces power when it is running. Reliability is key.
Makes sense. And regulatory hurdles.
And finally, yes, the regulatory framework, a major source of cost and uncertainty for any big energy project. Lengthy, complex licensing can add billions.
Nuclear fission certainly faced that.
It did, which is why the 2024 ruling by the U.S. Nuclear Regulatory Commission, the NRC, was such a big deal.
What did they decide?
They decided to regulate fusion systems under their framework for particle accelerators, not the much more stringent and expensive regulations for fission reactors.
Ah, that's significant.
Huge victory for the industry. It provides greater regulatory certainty and is expected to streamline the path to deployment, potentially reducing a major cost driver that has plagued fission for decades.
Okay, that regulatory clarity helps, but you mentioned competitors earlier. Fusion isn't competing in a vacuum, right? It's up against future energy prices, future technologies.
Exactly. That's a crucial point. Fusion's primary market role will likely be providing that firm, dispatchable power to complement intermittent renewables.
So its direct competitors are?
Other clean, firm technologies. Think advanced nuclear fission SMRs, new designs.
Small modular reactors, right?
Yep. Enhanced geothermal systems, which are pushing drilling tech.
Tapping deeper heat.
Right. Bioenergy with carbon capture, which offers that unique carbon negative potential. And, critically, long-duration energy storage solutions. If storage gets cheap enough, it could theoretically allow renewables to meet baseload demand themselves.
So if any of those get really cheap...
If any of those alternative technologies achieve significant cost reductions and deployment scale in the coming decade, the economic bar for fusion gets set much higher.
A moving target.
A constantly moving target. So strategic planning for fusion has to happen within the context of the entire clean energy innovation ecosystem. Its ultimate market share depends not just on its own progress, but also on the parallel advances and cost reductions of its future rivals. It's a dynamic race, not just against the clock, but against other promising solutions.
It's clear the economic hurdles are immense, but the potential rewards, well, they seem equally staggering. Okay, let's shift gears here. Beyond the immediate economics of the plants themselves, fusion offers this massive opportunity for job creation.
Absolutely, a whole new industry.
Yeah, when you think about it, we're not just talking about a new energy source. We're imagining a whole new economic sector, vibrant with high-skilled, well-paying jobs, potentially stimulating entire economies. What kind of jobs are we really talking about here, and what's the projected scale?
Some analyses predict the fusion energy sector could create over 1 million jobs globally by 2040.
Wow.
And that number continues to grow significantly as the technology reaches wider deployment in the decades after. To put that in context, this is part of the broader clean energy transition trend. IRENA, the International Renewable Energy Agency, estimates millions of net jobs globally by 2030, just from the shift away from fossil fuels.
So fusion adds another big layer to that.
A significant new layer, creating an entirely new industrial base. And the economic impact goes way beyond just direct employment at the power plants.
Ripple effects through the supply chain.
Exactly. A robust domestic fusion industry will require and stimulate a vast supply chain, creating jobs across really diverse industries. Think about advanced manufacturing for critical components.
Like the magnets and...
Those HDS magnets we discussed,
Yeah.
the massive vacuum vessels, precision-engineered plasma-facing components that have to withstand insane conditions, the high-power laser systems or radio frequency systems for heating.
Specialized manufacturing, okay.
Then there's material science and production.
Right.
Developing and fabricating specialized low-activation steels, tungsten alloys, ceramic composites needed for reactor construction materials that don't even exist in commercial quantities yet.
A whole field of materials innovation.
Huge field. And, of course, the sheer scale of construction and engineering. Building the power plants themselves, these are massive infrastructure projects. They'll need thousands of skilled workers for years. Civil engineers, pipe fitters, electricians, welders.
Standard construction trades, but on a high-tech project.
Exactly. And finally, a rapidly growing area. Software, and AI. For the incredibly complex control systems managing the plasma, for sophisticated plasma modeling to predict and optimize reactor behavior, and for predictive maintenance algorithms, which will be essential for keeping these plants running efficiently and reliably.
So it's a really wide net of expertise needed.
A very wide net.
That paints a really vivid picture. It's not just, the theoretical physicists designing reactors, but the skilled hands building, operating, optimizing them. It opens up so many different career paths. Could you, listening now, or someone you know, be part of this future workforce? What specific types of talent will be most in demand?
Exactly. The fusion industry needs a highly skilled and specialized workforce, but also a really robust pipeline of technicians and tradespeople. The demand for talent will be acute in several key areas.
Like what specifically?
We're looking at a strong need for fusion physicists and plasma scientists, obviously, to keep pushing the fundamental understanding and optimize reactor performance. Then nuclear mechanical engineers to design, build, operate the complex plant system's core, heat exchange, power generation.
The core engineering disciplines.
Absolutely. Material scientists are critical. We keep coming back to material. Developing and testing the next-gen materials capable of surviving that extreme fusion environment, often cited as one of the biggest hurdles. As I mentioned, data scientists and AI specialists will be in high demand for the complex computational models and control systems.
Managing the complexity. Okay, so we've covered the economic transformation, the jobs. Let's zoom out again to the biggest picture. How fusion fundamentally alters our entire energy system and tackles some of those massive environmental challenges. Fusion isn't just another power source. It sounds like a foundational technology.
It absolutely is. Let's start with a new paradigm for the electrical grid. Fusion's most critical role, arguably, is providing clean, firm, baseload power.
Clean and always on.
Exactly. Unlike intermittent renewables, like solar and wind, which only generate when conditions are right, fusion plants are designed to operate continuously. This dispatchable on-demand power is essential for maintaining grid stability and reliability, especially as we electrify more and more sectors like transport and heating.
The grid needs that stable foundation.
It desperately needs it, especially with high renewable penetration. Managing the variability of solar and wind is a paramount challenge. Without a reliable source of firm power to fill the gaps, grids would often have to rely on fossil fuel peaker plants, usually natural gas, to prevent blackouts.
Which undermines the whole point of decarbonizing.
Completely undermines it. Fusion is perfectly positioned to serve as this clean backbone for the grid. It's not a competitor to renewables, it's a crucial complement.
Working together.
Ideally, yes. A future energy system could see solar and wind providing the bulk of energy when available, with fusion plants providing that constant, unwavering foundation of power and ramping up to cover any shortfalls, ensuring the lights stay on reliably at all times.
Can fusion plants ramp up and down quickly?
That's a great question. Some advanced fusion plant designs, like Commonwealth Fusion Systems ARC, are actually being engineered for rapid ramp-up and ramp-down capabilities.
So not just baseload.
Not just baseload. They could potentially provide flexible load-following services, too, helping balance the grid second by second. That kind of flexibility from a clean, firm source,
Yeah.
that is truly a game-changer for grid stability.
Speaking of efficiency, the physical footprint is often touted as a huge advantage. How remarkable is fusion's energy density, really? And what does that mean for land use compared to other energy sources?
This is one of fusion's most compelling advantages. Its extraordinary energy density means the energy released from fusing atoms is literally millions of times greater than from chemical reactions like burning coal.
Millions of times.
Millions. To give you that concrete example again, just 1 kilogram of DT fusion-fueled deuterium and tritium can produce the same amount of energy as 10 million kilograms of coal.
That's staggering. It's hard to even visualize.
It is. And per unit of mass, the DT fusion reaction releases over 4 times more energy than a uranium fission reaction. So, the idea of powering a city with something physically tiny, like fuel equivalent to a postage stamp's weight over time, it redefines energy density.
And that density translates to land use.
Directly. This incredible energy density means a remarkably small physical and land use footprint for the power plant itself, while a big solar or wind farm needs vast tracts of land to collect diffuse energy.
Thousands of acres sometimes.
Thousands, yes. A fusion power plant is expected to occupy a space comparable to a conventional thermal power plant, or maybe a large commercial building. Think maybe a few hundred acres, not thousands upon thousands.
Ideal for populated areas or land-scarce regions.
Absolutely ideal. This advantage becomes really stark when you compare it Nuclear fission is already the most land-efficient electricity source we have.
Right.
According to U.S. government data and studies, a 1,000-megawatt nuclear plant needs about 1.3 square miles of land. To get the same electricity, a solar farm might need 75 times more land, a wind farm maybe 360 times more land, considering the total spacing area.
Huge differences.
Orders of magnitude difference. Other analyses looking at land use intensity like hectares per terawatt hour per year find nuclear is vastly more compact than renewables and fossil fuels. Given that fusion plants are expected to have similar or even higher power density than fission plants, they share this critical advantage of a minimal land footprint.
Addressing the energy sprawl issue.
Exactly. That's a significant environmental and social challenge of the energy transition. Where do we put all these energy facilities? Fusion offers a powerful solution to that.
Okay, so incredibly efficient space-wise, game changer for the grid. But you mentioned earlier, electricity is only about 20% of the world's final energy consumption. What about the other 80%? The stuff from fossil fuels for industry, transport. How can fusion help decarbonize beyond the grid? What about deep decarbonization?
This is where fusion's potential truly broadens, offering transformative applications far beyond just plugging into the wall socket. These non-electric applications could be even more impactful for deep decarbonization, targeting those really hard-to-abate sectors.
Where electrification is tough or expensive.
Exactly. Let's start with high-grade process heat for heavy industry.
Right, steel, cement.
Steel, cement, glass, chemicals.
Yeah.
Many critical industries rely on extremely high-grade heat, often over 1,000 degrees Celsius. This heat almost exclusively comes from burning fossil fuels today, making these sectors massive CO2 emitters and incredibly difficult to decarbonize.
How does fusion help?
Fusion reactors naturally produce extremely high-temperature heat. It's inherent in the process. Energetic neutrons get captured in the blanket surrounding the plasma, generating intense heat. This thermal energy could be directly supplied to adjacent industrial facilities.
Piping the heat next door.
Precisely. Replacing fossil fuels directly, eliminating huge amounts of CO2 emission. Imagine a new generation of fusion industrial parks, the clean energy source right next door to the factories it powers. A truly integrated, clean industrial ecosystem.
That's a powerful vision. What else beyond heat?
Okay, next up. Clean hydrogen production at scale. Fusion energy is potentially an ideal power source for unlocking the hydrogen economy.
Hydrogen is talked about a lot.
It is, but producing clean hydrogen, especially via electrolysis of water, is very energy intensive. Fusion can provide both the vast amounts of electricity and the high-temperature steam needed for advanced, highly efficient methods like high-temperature steam electrolysis, or HTSE.
HTSE. How does that work?
By using fusion-generated heat to create steam directly for the electrolysis process, HTSE can produce hydrogen with significantly less electrical input compared to conventional electrolysis. Makes it much more economical.
Cheaper green hydrogen?
Potentially much cheaper, yes. This could enable green hydrogen production at a scale and cost that makes it viable as a clean fuel for things like long-haul shipping, aviation, as a chemical feedstock for industry making ammonia for fertilizers, for example, and as a medium for long-term energy storage.
Displacing current carbon-intensive hydrogen production.
Exactly, which is mostly from natural gas right now and a major source of CO2.
Okay. Heat, hydrogen, what else?
And then there's water security through fusion-powered desalination. Access to fresh water is one of the most pressing global challenges of this century.
Absolutely critical.
Water desalination, removing salt from seawater, offers a nearly limitless source of fresh water, but it's hampered by its enormous energy consumption. Makes it prohibitively expensive for widespread use currently.
Too costly for many places.
Right. The prospect of abundant, reliable, low-cost energy from fusion could be a complete game changer here, making large-scale desalination economically feasible for the first time.
The implications would be huge.
Profound. Fusion-powered desalination could secure water supplies for coastal cities, arid nations, potentially ending water scarcity for millions. Beyond just drinking water, it could enable massive agricultural projects in desert regions, turning barren land into productive farmland.
Greening the desert, literally.
Literally. It could even support ambitious geoengineering projects, like irrigating vast new forests to act as living factories for carbon sequestration.
That's thinking big.
It is. And finally, let's not forget deep space exploration and propulsion.
Right, the sci-fi application.
It sounds like sci-fi, but the immense energy density of fusion makes it a truly revolutionary technology for deep space travel. Current chemical rockets are limited by propellant mass and speed.
Takes years to get anywhere far.
Exactly. Fusion rockets, in contrast, could provide highly efficient, sustained acceleration, dramatically cutting transit times. A fusion-powered trip to Mars could be done in a fraction of the time a trip to Pluto, cut from over a decade to maybe just 4 years.
How would that work? Fusion reactors on rockets?
Two main concepts: nuclear electric propulsion, NEP, where a compact fusion reactor generates lots of electricity to power highly efficient electric thrusters, like ion thrusters.
Powering advanced engines.
Or, even more advanced, a direct fusion drive, where the hot plasma fusion exhaust products themselves are directed out of a magnetic nozzle to provide thrust directly. Extremely high efficiency, potentially.
Using the reaction itself for thrust.
Yes. Plus, a fusion reactor provides ample onboard electrical power for instruments, life support, communications, overcoming the limits of solar panels in the dim outer solar system. Companies like Pulsar Fusion are actually developing concepts now, aiming for in-orbit demos later this decade.
So not just sci-fi anymore.
Moving towards engineering reality. This dual capability, clean electricity, and high-temp heat fuels propulsion is a unique advantage distinguishing fusion from almost all other clean energy sources. It broadens its strategic value way beyond just replacing coal plants.
That's truly a visionary scope, extending way beyond Earth. But let's bring it back to that core promise. Fusion is often hailed as the ultimate clean energy source. Let's dig into what that really means for its environmental and safety claims. What does clean truly encompass here?
It means a fundamental paradigm shift, really. In terms of climate change mitigation, the direct operation of a fusion reactor produces zero carbon dioxide or other greenhouse gases. Full stop.
Zero direct emissions.
Zero. The DT reaction itself yields only an inert, non-toxic helium nucleus and a neutron. The only direct byproduct is helium, which is harmless and can even be captured for industrial use.
Okay, but what about the whole life cycle? Building it, fuel, decommissioning?
That's the right question. No energy source is truly zero carbon across its entire life cycle. A life cycle assessment, or LCA, accounts for emissions from manufacturing, construction, mining lithium for fuel breeding, decommissioning, etc.
So how does fusion stack up in LCAs?
Studies conducting LCAs for fusion power plants project that its total life cycle emissions will be very low, genuinely on par with nuclear fission and renewables like wind and solar.
So comparable to the best we have now?
Yes. One analysis concluded CO2 emissions from a tokamak fusion reactor would be less than utility-scale solar PV and less than double those of a fission reactor. And importantly, as the industrial process is used for construction steel, concrete get decarbonized themselves.
Using clean energy.
The life cycle emissions of future fusion plants are expected to fall even further. So it's not just zero at the point of operation, it's extremely low across its entire lifespan.
That addresses the carbon footprint, a huge benefit. But what about safety? When people hear nuclear, they immediately think, Chernobyl, Fukushima, meltdowns, hazardous waste. Is fusion truly different in a fundamental way? Can we genuinely say it's inherently safe?
Yes, we absolutely can, and it's arguably the most crucial distinction from nuclear fission. Fusion reactors possess what's known as inherent safety.
Inherent safety.
Meaning their safe operation relies on the fundamental laws of physics, not primarily on complex engineered active safety systems that could potentially fail.
Physics itself prevents the worst-case scenario.
Exactly. The fusion process is fundamentally different from a fission chain reaction. Fission relies on a self-propagating chain reaction that must be actively controlled and cooled to prevent it from running away. Fusion, conversely, is incredibly difficult to even start and sustain. It needs that delicate balance of extreme temperature, pressure, magnetic confinement.
Hard to keep going, not hard to stop.
Precisely. So here's the key accident scenario. If any of those precise conditions are disrupted, a malfunction, power loss, earthquake, whatever, the plasma immediately cools down, loses confinement, and the fusion reaction simply ceases within seconds.
It just stops?
Just stops automatically. This means a runaway reaction or nuclear meltdown, the primary safety concerns for fission reactors, is physically impossible in a fusion device. Furthermore, the amount of fuel actually in the reactor chamber at any moment is minuscule, just a few grams, like the weight of a postage stamp. Far too little to fuel a large-scale energy release in an accident. There's simply not enough fuel present to cause a major incident.
Okay, so meltdown risk is off the table. What about waste? Fission leaves that long-lived, nasty stuff. Does fusion have waste?
Yes, it does produce waste, but it's fundamentally different. Fusion energy does not produce the high-level, long-lived, radioactive waste-spent fuel rods containing fission products like cesium-137 or strontium-90. That's the main environmental liability of fission.
No spent fuel rods needing deep burial for millennia.
Correct. The primary source of radioactive waste from a DT fusion reactor is neutron activation. Those high-energy neutrons produced in the reaction bombard the structural materials of the reactor vessel, the steel, other components.
Making the reactor structure itself radioactive.
Exactly, causing some of the atoms in those materials to become radioactive.
So how hazardous is that activated material?
While the initial volume might be larger than fission waste, its characteristics are very different. It's classified as low to medium level waste, posing a much lower risk to health and the environment. Most importantly, the radioactivity decays much, much faster.
How much faster?
The majority of the activated components would become safe enough to handle, usually with remote equipment, and potentially be recyclable within, say, 50 to 100 years, not the tens of thousands or hundreds of thousands of years required for fission waste.
100 years versus 100,000 years. Big difference.
A massive difference. And a key goal of fusion materials science is developing advanced low-activation materials, things like vanadium alloys, silicon carbide composites, specifically designed to minimize neutron activation in the first place, further reducing the waste burden, maybe even allowing recycling sooner.
Engineering the waste problem away as much as possible.
That's the goal.
What about proliferation? Nuclear weapons risk. Fission has that connection.
That's another area where fusion offers a significant advantage. The proliferation and security risks are considered very low.
Why is that?
Fusion power plants do not use or produce fissile materials like highly enriched uranium or plutonium, which are the key ingredients for nuclear weapons. The DT fuel cycle uses deuterium, which is stable hydrogen, and tritium, which is radioactive hydrogen.
Tritium is used in weapons, though, isn't it?
It is a component in modern thermonuclear weapons, yes.
Right.
But the quantities involved in a fusion reactor are relatively small, and crucially, it's produced and consumed on-site in a closed loop bred from lithium inside the reactor and immediately fed back in as fuel.
So no large stockpiles lying around.
Exactly. There's never a large stockpile of tritium, and the amount in the reactor at any one time is far too small to be useful for a weapon. Plus, while it's theoretically possible, you could try to use fusion neutrons to breed plutonium from a uranium blanket.
Sneakily making bomb material?
It would require a complete, extensive redesign of the reactor that would be easily detectable on an international monitoring. So for these reasons, fusion is really not seen as posing a significant proliferation risk.
Okay, that's reassuring.
So fusion's cleanliness isn't just a fortunate byproduct. It's really an engineered outcome. While the core physics is clean, the long-term environmental sustainability and public acceptance absolutely hinge on solving that materials science challenge. Developing advanced, low-activation materials that can withstand the environment for decades and be safely recycled is just as important as getting higher plasma temperatures or stronger magnets. This means a credible fusion strategy must prioritize materials, research, and building dedicated test facilities, like that proposed fusion prototypic neutron source, FPNS, equally with the plasma physics experiments.
You need to test the materials properly.
You absolutely do. The environmental case for fusion is incredibly strong, but it has to be secured through deliberate, robust engineering.
It's clear the potential is immense, safety and environmental benefits compelling. But let's be realistic. The path to commercial fusion isn't a straight line. There are huge hurdles, often called the valley of death.
The gap between lab and market.
That gap between experimental success and actual commercial viability. Can you elaborate on what specifically stands in the way? And maybe use technology readiness levels, TRLs, to map it out.
Yeah, the valley of death is a very apt term for this stage. It's that perilous gap between demonstrating something cool in a lab and deploying it as a reliable, cost-effective commercial product that people can buy. To assess maturity objectively, the technology readiness level, TRL scale, is really useful. It's that 1 to 9 scale used by NASA and the DOE.
Right, 1 being basic idea, 9 being fully operational.
Exactly. So if we look at fusion through that lens, TRLs 1 to 3, research, basic principles observed, proof of concept. The fundamental physics of fusion plasma is largely here. NIPS ignition arguably pushed towards TRL 4.
Okay, basic science proven.
Then TRLs 4 to 6. Development. Component validation in labs, then relevant environments. Many critical fusion technologies are here. HTS magnets, validated at scale in a lab, maybe TRL 4 or 5. ITER is designed to test key components, diverter, breeding blankets, and hopefully get them to TRL 6 or 7.
Testing the key parts.
Right. Finally, TRLs 7 to 9, deployment. System prototype demo in an operational environment, qualified system, proven mission success. Critically, no integrated fusion system is anywhere close to this level yet.
The whole package isn't ready.
Not even close. A first-of-a-kind commercial power plant represents that leap to TRL 8 or 9. This TRL assessment reveals the critical gap. While the core physics is advancing, the essential engineering technologies needed to build a durable, efficient power plant materials, heat exhaust, fuel cycle are at much lower TRL. Closing these engineering TRL gaps is the central task now.
What an incredible story of engineering and technology. From the science breakthroughs to this dynamic global race, the potential impact on our grid, jobs, resources, even space. It's really something.
It's a remarkable story unfolding.
Connecting it to the bigger picture.
If we connect it to the bigger picture, the profound impact of fusion extends so far beyond just electricity. It really is a foundational technology for decarbonizing our entire economy, for securing vital water supplies for a growing world, for expanding humanity's reach into the cosmos. It genuinely promises energy abundance without compromising the health of our planet.
So the question has shifted.
The debate really isn't if fusion is possible anymore. It's how and when it will be deployed. The decisions made in this decade by policymakers, by investors, by the dedicated scientists and engineers working on this, those decisions will absolutely determine the timeline, the trajectory, and ultimately the profound impact fusion will have on your future.
It's a powerful thought to leave you with. The power of the stars is genuinely within our grasp. But harvesting it, that's going to require the very best of human ingenuity, perseverance, and collaboration.
Indeed, it's an incredible journey.
Thank you so much for joining us on this deep dive into the societal impacts of viable fusion energy. We'll be keeping a very close eye on this, and we hope you will too.